Hey everyone, and welcome. Today, we are diving headfirst into one of the coolest, most powerful parts of AI, reinforcement learning. It's basically all about teaching machines to learn pretty much the same way you and I do, through a whole lot of trial and error.
So that really gets us to the heart of the matter, right? How in the world do you actually convince a bunch of code to, learn from its own mistakes, to figure out what works and what doesn't, and get better all on its own? Well, that's the exact puzzle that reinforcement learning sets out to solve.
All right, here's the game plan for our guided tour today. We're going to start with the big idea, then look at the formal rules of the game. After that, we hit a huge fork in the road in how these things learn, so we'll dive into some of the most famous algorithms down each path. Then we'll see RL out in the real world and wrap up with a kind of user manual for when you should and shouldn't use it. Okay, so at its core, reinforcement learning, or RL, is really just a simple feedback loop. You've got your agent, that's our learner, and it's living inside an environment. The agent takes an action, and the environment gives it back a reward. Think of it like getting points in a video game. The agent's one and only goal? Get the highest score possible. After trying things out, millions of times, it starts to build up a strategy, what we call a policy, for how to act to get the most rewards. Now, to get this all working with math and code, we need a formal rulebook. And in RL, that rulebook is called a Markov Decision Process, or MDP. Yeah, I know, it sounds super complicated, but don't worry about the name. Just think of it as the official way we describe any RL problem, and it's made up of a few key pieces. First up, we've got the state space. This is literally just every single possible situation the agent could find itself in. Let's use chess as an example. The state space would be every single legal arrangement of pieces on the board. We're talking a ridiculously huge number, but it is a specific defined set. So if the state is where all the pieces are, the action space is the list of all the legal moves you can make from that state. For a little pawn, that might just be moving forward one or two spots. For a queen, well, her menu of options is a whole lot bigger. It's everything the agent is allowed to do at any given moment. And here we have what is arguably the most important part, the reward function. This is the feedback. It's the whole scoring system. You capture your opponent's queen? Great. Here's a big positive reward. You get checkmated? Ouch. That's a massive negative reward. The agent's entire learning process, everything it does, is driven by one simple goal: make that reward number go up. Okay, so now we've hit the first really big strategic choice in the world of RL. Does our agent try to build its own internal map of how the world works, or does it just learn purely from raw experience without trying to understand the why? This decision, believe it or not, is the most fundamental fork in the road. On the one hand, you have model-free learning. This is a lot like learning to ride a bike. You don't sit down and study the physics of balance and friction, right? No, you just get on and learn by falling over. A lot. The agent doesn't know why an action works, it just knows that it works. On the other hand, you've got model-based learning. This is like using a GPS to navigate a new city. The agent first learns the rules of the road, builds an internal map of its world, and then uses that map to plan out the best route. So let's head down that model-free path first. It's actually the more common approach, and there are a few different ways an agent can learn without ever building a map. Think of this as a quick cheat sheet for the three main strategies. First, value-based methods. They focus on figuring out exactly how good it is to be in any particular situation. Then you've got policy-based methods, which kind of skip that step and just try to directly learn the best action to take. And finally, actor-critic methods, which are a really clever hybrid. You have one part, the actor, that does things, and another part, the critic, that basically says, hey, that was a good move, or nope, that was a terrible move. Our first deep dive is a true classic from the value-based family, Deep Q Networks, or DQN. This is the legendary algorithm that taught itself to play old-school Atari games by literally just looking at the pixels on the screen. And yeah, it got way better than any human. So what was the secret sauce that made DQN work? It was a genius trick called experience replay. See, the problem is, if a neural network learns from its experiences one after the other, it gets really unstable. It becomes obsessed with the last thing it saw. Experience replay fixes this with a really neat memory hack. Here's how it works. As the agent is playing the game, it saves every single experience, the state it was in, the action it took, the reward it got, into this giant memory bank. Then, instead of learning just from its very last move, it reaches into that bank and pulls out a random handful of past memories to train on. It's kind of like studying for a test by using a shuffled deck of flashcards instead of just reading a textbook from front to back. This simple trick shuffles the data, breaks the patterns, and makes the learning process so much more stable. Okay, now for a look at the actor-critic family and an algorithm that is, no joke, powering some of the most advanced AI on the planet today. Proximal Policy Optimization, or PPO. This guy is a key player in training the huge language models we all use. Its big idea is to basically act like a safety rail. It stops the AI from changing its strategy too much, too fast. One huge, overly ambitious update can completely ruin everything it's learned. PPO prevents this with a technique that has a truly terrifying name, a clipped surrogate objective function. But honestly, all you need to remember is that it forces the AI to take small, careful, stable steps. No giant leaps. And that stability is absolutely critical for unbelievably complex jobs. It's the reason PPO is at the heart of something called reinforcement learning from human feedback, or RLHF. When you're trying to fine-tune a model like ChatGPT based on what humans prefer, you have to make those tiny, stable updates. You can't risk a drastic change that sends the whole thing off the rails. All right, time to switch gears. Let's head back to that fork in the road and explore the other path, model-based learning. This is where the agent meticulously builds a map of its world. And in this category, there is one undisputed heavyweight champion, AlphaZero. The magic of AlphaZero is how it combines two things. First, it has a perfect model. It knows all the rules of the game. But second, it combines that with a powerful neural network that acts like intuition. The network looks at the game board and guides a powerful search algorithm, telling it which moves look promising and who seems to be winning. It's this beautiful dance between raw brute force calculation and a deeply learned intuition. And the results were just mind-blowing. AlphaZero didn't just learn to play chess and Go. It basically rediscovered centuries of human knowledge on its own and then invented completely new, almost alien-like strategies on its way to becoming the greatest player the world has ever seen. Now, that same idea, combining search with learned intuition, is being used to solve really hard real-world problems. So, after this whole tour, we get to the really practical question. Let's say you have a problem you need to solve. Is reinforcement learning actually the right tool for the job? Well, RL really shines when a few things are true. It's great when you have a good simulator, a place where an agent can try and fail millions of times without any real-world consequences. It's also perfect for problems where today's actions have complicated, delayed effects down the road. But you have to watch out for the pitfalls. RL can be incredibly slow to learn. It needs a ton of data. And for those model-based systems, if that internal map is even a little bit wrong, it can lead the agent to make really confident but totally disastrous decisions. So, what's the big takeaway from all this? Reinforcement learning isn't just a single algorithm. It's a whole way of thinking. It's a powerful framework for tackling any problem that involves making a sequence of smart decisions to reach a goal, whether that's in a game, a robot, or an AI assistant. And that leaves us with one last thing to think about. For most of history, we've solved problems by programming the solution, step by step. Reinforcement learning flips that on its head. It asks a different question. For the truly massive challenges ahead of us, what if the best path forward isn't to write the answer ourselves, but to build a system that's capable of discovering that answer on its own?